The title of our webinar today is Object-Based SAR Analysis, and we'll be giving you a case study on multi-temporal wetland mapping using the object-based SAR image analysis capability. Today's presenters are myself on the left, Kevin Jones, Director of Marketing, and Jason Flatt, who's one of our technical solutions specialists here at PCI Geomatics. This is the first in a detailed webinar in a series of webinars that are focused on the latest and greatest technology that we have released. So this particular one is a follow-up from roughly 2 weeks ago. We gave an overview of the 2018 release, and this webinar plus others are planned. We'll be looking at DSM True Ortho, we'll be looking at in-SAR processing, multi-sensor mosaicing, and also analysis-ready data tools for multi-temporal analysis. So those are coming up. Look out for announcements about those, and be sure to register through our website to attend those future webinars. So just a quick outline about today. So we'd like to first of all just give you a brief outline of the capabilities that are available within our technology. We do support multiple missions. We want to just briefly explain some of the different products that could be generated, and we also want to touch upon the RadarSat constellation mission support, which is coming up, and tell you a little bit about that satellite and what we will be doing. Then we'll get into more details about radar-based object analysis. So we're nicknaming it OBSAR, so object-based synthetic aperture radar analysis. And after that, I'll pass over to Jason, and he'll give you a detailed demonstration on the new tool and how it can be used to process radar imagery. So one of the key things with our latest and greatest technology is that we have added support for multiple areas within SAR. So one of the key things is adding support for different sensors. There are more and more missions being launched and more data being distributed and made available. So we definitely continually add sensor support over time. Georeferencing, so being able to position those images correctly on the ground so that if you're performing any kind of analysis and comparing that with other data sets, obviously you need to position those images correctly on the ground. Radargrammetry refers to the ability to generate elevation models from same-side stereo radar images that are collected with sufficient parallax. We do support calibration of different data sets, and also we support natively complex formats, which is very important for a lot of the work that is done on radar data because we are working in the complex image domain very frequently. Polarimetry is something that we have added for many, many years with RadarSat 2 and other dual pole or multi-pole SAR missions. We definitely have that capability. We added actually over 2.5 years ago compact polarimetry in anticipation of the RadarSat constellation mission, as well as other compact pole missions that are currently available and are planned very soon. So we do have support for compact polarimetry. The SAR polarimetric target analysis is a capability that's been there for several years to allow you to perform classification and detection of different objects based on their radar signature. And then interferometric SAR is another key capability that's been added. So as you can see, we really have a well-rounded capability as it relates to SAR, and it's definitely an area that gets a lot of attention here at PCI in terms of our development efforts. Just a quick taste of the different sensors that we support. These are not by any way representative of the most utilized satellites. They just happen to be sorted alphabetically. So we have some of the different sensors. You can click on that link, or you can go search up Geomatica sensor support or PCI Geomatics sensor support, and you'll land on a section on our page that breaks down what sensors are supported for different processing levels. And you can see here that initial table that I had, some of the same information is represented. So can we collect, can we georeference or orthorectify the data sets? Can we extract stereo elevation models from them? Can we use SPTA or target analysis? And can we do in-SAR processing? So if you're curious to see if we support a particular satellite and what specific level we support, I encourage you to look that up on our website or through our technical specifications. We have a lot of great info about that. Now, one of the new things that is becoming very, very important in the context of the RADARSAT Constellation mission, which is going to be launched early in 2019, is compact polarimetry. So I won't go into a detailed explanation of compact polarimetry, but suffice it to say that the real benefit of the RADARSAT Constellation mission is the fact that there will be 3 satellites flying in tandem and collecting data. So standard coverages are really going to be rich in terms of their spatial extent and their temporal extent. And one of the decisions that was made in terms of how those instruments were built was to limit the construction of the SAR antenna to only have one transmit module, which means the satellites can only transmit in one particular polarization or in a circular polarization, and then they can receive in with 2 different receivers. So what this graph is showing is basically a full polarimetric data set, a full quad pol data set on the top, and some different products. So Freeman-Durden decomposition and highlighting double bound surface refraction and volume refraction. And on the bottom, we have a simulated RADARSAT Constellation mission product that we can generate in Geomatica. So if you have a full quad data set today, you can use it to generate a quad or a compact pol data set. And then you can run similar analysis to see what the difference will be in terms of extracting information. And as you can see, the three illustrations on the screen are a pretty close match. The double bounce on the top and the bottom, the surface refraction and the volume refraction concur with each other very strongly. Just a few words about our technology. So a lot of people know PCI for the desktop offering, but over the last several years, we've produced technology that is very, very scalable and very flexible. So the idea of Geomatica being a platform is definitely something that is very much true. There is a Python API built into the software, which allows you to build workflows within the desktop software environment. And if you wanted to automate a specific workflow, you could even use something like a Docker container on the Amazon cloud to package data and software to execute a specific task using cloud infrastructure. Or the same way that you could deploy a GXL workflow. GXL is our large volume production system, where really you're trying to produce data at scale. So if you're, for example, 50,000 images being processed in the matter of a few days or a few hours is not unfeasible using something like GXL, depending on the architecture and the workflow. So really our solutions they're flexible, they're scalable, depending on whether you're working with a small number of data sets or really large data sets. Geomatica, think of it as a platform as opposed to a desktop tool only. So we want to launch a quick poll to kind of gauge who's here today and hopefully provide you some good information. So we just want to get a sense of what data sets you're currently using. So what SAR imagery do you primarily work with? So is it the RADARSAT constellation, whether that's RADARSAT 1 or 2 or the RCM? Maybe it's Sentinel or ComSat, which is a satellite out of Korea. Perhaps you're using the Airbus sensor, TerraSAR or TandemX. And if you're using another SAR sensor, we'd love to hear which one. You can definitely use the questions panel, which is available to you, to type in whatever sensor it is that you're using. So I'll leave that open for just a couple more moments and then I'll move on with the presentation. So I'll just have a quick look here. Looks like the majority of people have voted, so I'm just going to close that down in 3, 2, 1. And I'll just share the results on the screen right now so you can see that. So it looks like quite a few of you are using Sentinel-1. And then second place is RADARSAT, the RADARSAT series of sensors, and then TerraSAR TandemX. So kind of interesting to see those results. Thanks for giving us that insight. So I just want to quickly go now to Object Analyst and some of the new capabilities. Those of you who are familiar with our technology will know that in the last year and a half, so roughly in April of 2017, we introduced object-based image analysis. And at the time, we primarily focused on optical data. However, having such great expertise within our toolkit to process SAR data, we have been able to develop technology to specifically handle SAR data in terms of segmentation, classification, and data preparation, and so on. So over the next few slides, you'll get a sense of really our design objective was to provide you with an environment that makes it more easy to work with radar imagery. So radar imagery can be a little bit more difficult to work with. It doesn't look like optical imagery. Sometimes it's distributed in particular formats such as slant range. And depending how you're looking at that data or what analysis you're doing, you need to prepare the data, do some pre-processing. So we've tried to streamline that for the user to make it a little bit more accessible to work with data sets. And what we're working with today is a set of fully polarimetric images where a lot of that pre-processing is done on the fly, which was sort of a key part of our design with this tool. So as I mentioned, we within OBSAR, we're leveraging the SAR data for object-based image classification. We support a variety of data types, could be fully quad pole, dual pole, or single pole. And we take care of the calibration. So if you want to apply a sigma naught or a beta naught calibration, you can definitely do that if you're used to working in that domain. And some other things that we take care of is the speckle filtering. So as you'll see, radar data tends to be a little bit more heterogeneous in terms of certain classes, and so it's a little bit more difficult to interpret. So filtering, adaptive filtering to retain the radiometry, but to perform proper scientific analysis and not alter the data is a very critical part of image analysis for radar. Well, we also take care of tail trimming, so removing, again, some of that noise that's inherent in SAR data sets. And as you'll see, SAR specific attribute calculation. So if you think of regular object-based with optical imagery, you might take the mean value of an infrared band or the mean value of an NDVI, a derivative product that you've calculated. So there are specific indices or parameters that can be extracted from particularly radar, quad pole radar data that can really be useful for classification. And so you'll see how that's done in our tool in the demonstration. Just some other things that have been added. So if you are someone who has a lot of reference information from the field, whether it's you personally went out to the field and collected GPS point data that reflects specific classes, or you're using a reference data set that's been produced by a third party, you can bring that into the system and you can train the algorithm to be used for the classification. So this is a nice way to pick your training sites as you're performing supervised image classification. There's specific ways that we handle the data. So we resolve conflicts in the case where you have multiple points that represent different classes in the same segment. We have ways of handling that, and we provide you with those options. Just a quick look here, we do also have segmentation by region of interest. So sometimes segmenting an entire image is time consuming. So with this version, you can basically bring in a vector shapefile or a vector data set that represents an area that you're interested in testing. So here we have 3 different locations that we're trying to see how the segmentation parameters are going to produce results. So we can run that and sort of get a sense of whether the objects are the right size and if we can tweak some of the parameters based on what we're trying to accomplish. So that's kind of a nice feature, allows you to work a little bit more rapidly. And the workflow for OBSAR that Jason's going to be walking you through consists of the following. So Jason will basically be working with data that's sitting on disk that's in the distribution format of the vendor. So in the case of RADARSAT-2, that's the raw data with the product.xml. We can ingest that data and orthorectify it. We retain all of the important metadata as we're going along. I think where Jason's going to pick things up today is he won't be showing you those pre-processing steps. He'll be running directly from the segmentation, and then he'll do the attribute collection. He'll show you how to use ground sample data for attribution of training sites, in addition to selecting certain polygons for training. And then he'll also show you some rule-based adjustments that can be made to the data. And then some final steps in terms of reforming the outputs. This is just showing you once again the panels, which you're going to see live in a minute. So we process the data on the fly. So you can see that when we point to a product.xml in the case of RadarSat-2 data, we're prompted with the choice whether we want to do sigma naught, beta naught, gamma, or no calibration. We can select the channels. So that's we automatically detect that it's a RadarSat-2 data set in this case with full quad data. And then the SAR pre-process button is also activated based on the type of data that you're providing to the system. So if you're providing a full quad data set, then it's going to expose to you some of the adaptive filters that could be applied, whether it's the enhanced Lee or the PS boxcar. So that'll help you for your analysis. It'll smooth some of the surfaces. It'll remove some of the noise in the data. And then another aspect of the pre-processing, which is done on the fly for you in the background, is tail trimming. So as you can see, the histogram here at the bottom of this slide, the majority of the data, so like 85% of the data is within a certain area. So we can tell the system, anything that's greater than 85%, trim that off and don't take it into account. So again, because radar data tends to be noisy, we can specify a tail trim for our analysis. This is just showing the segmentation comparisons. So we have here basically just showing scale parameters that are changing. So we've got 25 on the left at the top, 15 on the right, 50 on the bottom right, and then 50 on the bottom with some differences. So differences in terms of the size of the filter before, differences in terms of the scale parameter. So you can see that we can play very easily with different filters and different scale parameters or shape and compactness, and see what kind of objects we're getting. And the algorithm does quite well to delineate radar data, which is not a simple thing. And the nice thing about all of this is you're in the complex domain. You're not having to project the data and ground range and orthorectify and throw away a lot of useful information. So we're working in the complex domain with SLC data, and we're able to do a lot more and extract really the maximum value out of the SAR data. The attribute calculation step is very similar. However, what I'll call your attention to is there's a specific SAR pull down here. So these are all what we consider to be probably the most useful polarimetric parameters that can be used, that are complementary as opposed to overlapping in terms of the information that they can extract from the data. So we expose all of those. You can select specific ones that you're used to working with, or you can select all of them. Basically, once you select the bands and you select the polarimetric attributes to compute, it will just add those values to the table in your segmentation file. For dual pol data, obviously the polarimetric decomposition parameters are not exposed. However, you can calculate some other SAR texture measures, such as mean, standard deviation, entropy, and so on. So the workflow is going to consist as what you see on the screen. So the segmentation is what you see, and then you see some training sites and some specific classes. And really, we're going to try to leverage existing ground truth data, import that in, and conduct the classification. Once again, Jason's going to be giving a live demonstration in a second here. This is just the result once we've done the training, and so what the resulting map is going to look like. And then the final step, which is the reforming of the shape. So you can see that all the polygons that touch each other that are the same class have been dissolved into one big polygon, so it looks a lot nicer. So I'm going to launch one more poll, and then I'm going to pass over to Jason. So just curious about what you're planning to use SAR imagery for, like what application or what you're doing right now. So Is it land use line cover mapping as it relates to agriculture or what specific agriculture or forestry? Are you looking to use SAR data for monitoring and change detection? Maybe you're more on the military side and you're looking at detecting objects and leveraging radar data for that. Again, maybe more on the military side and you're looking at maritime domain awareness. You know, there's multiple uses. These are just some of the potential uses of SAR data. Of course, it's on an exhaustive list. But if you have another application area that you're working on, we'd love to hear about it. You can fill in the questions panel once again. So it looks like the majority of you voted. I'm going to close that down in 3, 2, 1. And I'll just share those results with you as well. So you can see that quite a few of you are doing monitoring or change detection. Of course, radar is very well suited for that because it can collect data through clouds and day or night. And then the next kind of group is looking at land use line cover mapping. All right, at this point, I will pass over to Jason. And he's going to walk you through his case study.
Hello, everyone, and welcome. Today, we'll be going over a multi-temporal wetland feature extraction. And to give just a brief overview, a case study of this wetlands. So wetlands are critical parts in the natural environment and are hotspots for biological diversity, especially in Canada. But the problem is that our wetlands are facing pressures from human activities, invasive species, and climate change, and an array of other pressures. So proper management procedures and observation practices will be necessary for us to ensure wetland preservation and protection for the future. So we can leverage multi-temporal SAR imagery to develop wetland land cover classification maps, water cycle changes, and long and short-term change detection. So the benefits of SAR data. Why would we use SAR imagery for the wetland feature extraction? Well, a number of reasons. First is it is an active sensor. That enables us to have consistent monitoring of the area regardless of the weather conditions. This will then enable us to collect imagery based upon the water dynamics, such as dry and flooded periods, rather than being forced based upon the weather. This temporal difference will then enable us to identify wetlands in relation to other vegetated surfaces. And next is physical response. So the actual response to the SAR energy with the vegetation will actually enable us to help extract specific classes. Now, Kevin's already gone into detail about the workflow, but just to give a brief overview of the demonstration, we're going to be working with 2 SAR images, one collected in April during the flooding period, and the second during the dry period in July. I already ran a SAR ingest and orthorectification to ensure the proper overlap between the 2 images. As SAR imagery, though, does come in many formats and processing levels, the system is actually able to identify the type of radar or SAR image based upon the image's metadata. The OA system will then be able to read through the metadata, determine the available pre-processing parameters to apply, and which SAR attributes that can be attributed. I would then run the segmentation, collect attributes based upon both dates, the different quad pole parameters, and then collect training sites for 7 different classes. The first will be consisting of developed land, which will contain agriculture and urban areas. The second is swamps, water, forest, and then 3 different types of wetlands. And lastly, I'll run a supervised classification and then use rule-based conditions to refine the classification. Now for the demonstration. Just want to show the area of the 2 RadarSat images. The first area, or the first image, is from July. We can see the area is vegetated, and based upon the different reflectance, it's different types of wetland vegetation. And then we can look at the April date and see that the whole area has been flooded. So this area we see is going to be wetland, and we can utilize our process to identify the wetlands. As Kevin mentioned, we have the new area of interest tool. So we're going to be running our entire segmentation within this area of interest and leveraging our ground truth import tool by using an agricultural data set developed by the Quebec government. Now, the first step to running our object-based our feature extraction will be to open up the Object Analyst tool, which is located in our analysis dropdown. You can select the Object Analyst. And here we see two tabs. The operation, which is a drop-down list of all the different operations we can run through. And depending upon our workflow, we may use all or only a few of the operations. And then the processing canvas, which will document all of the operations we run. And if we want to, we can go back and actually edit our operations and rerun them, just to help with testing. So the first operation is our segmentation. And we're going to be segmenting based upon the July data because we want to leverage the vegetation that's present rather than the April imagery where it's all flooded. So we've selected the July data, and already all the channels have been identified and selected. Now, for the interest of time, I have already pre-processed all the data, but I will show you all the steps required to get to the result. So once I have loaded the image and I have selected all the channels, I can select OK, which will then allow us to perform our SAR pre-processing. We can open up the SAR pre-processing. We have the option for filter type and tail trimming. And the tail trimming is important because it minimizes the effect of backscattering, as frequency histograms related to SAR data are often characterized by strong outliers in the rightmost tail, as you saw in that little graph provided by Kevin. And these outliers can have a strong negative influence on the segmentation results. So this tail trimming removes that. So I'm going to leave the options as default and select OK. For the area of interest layer, I'm going to select the AOI that we have visible. Let's choose AOI. I'm going to set the scale, the shape, and compactness. That's to the parameters as displayed in the workflow slide. Choose an output, set the layer name, and then add it to the processing canvas. If I wanted to run the whole procedure, I would go add and run. But I'm just going to add it. And we can see all the parameters that we set are loaded in, and we can always go back to them if we wanted to perform further testing. Now, after we run the process, segmentation will be displayed over here. We can zoom in and see the whole area has been segmented based upon all the data we selected. And we can then perform our second operation, which is the attribute calculation. I've already selected the July dataset, which identifies the 4 quad pool bands. And because it's identified as quad pool, we now have all the polarimetric SAR options. Now, what's important is that the specific SAR attribute calculations that are included will leverage our SAR specific analysis. And there's 2 options: the texture attributes, which can calculate the texture measure based upon second order statistics from the gray level concurrence matrices. We're going to be working with the polarimetric attributes available for fully polarimetric images only. And these attributes correspond to a selection of parameters from various polarimetric decompositions that will actually have the potential to help us discriminate among diverse sets of land cover classes. Now, I'm going to open up the polarimetric SAR attributes or calculations. I'm going to choose entropy, anisotropy, double bounce, volume scattering, surface scattering. And then I'm going to run the process. And I'm going to do that procedure twice for both dates so we can leverage the temporal difference. And if we open up the attribute table, they will be loaded in. Close that. The next operation, because we're going to run a supervised classification, we're going to make use of training sites. And not just training sites, we're going to leverage that external data set from the Quebec government. So I'm going to zoom out again, and I'm going to showcase the ground truths. Now, the data for ground truth import must be set to point data type. As such, I created the centroids and set a class set for agriculture. I can display over here. We can scroll all the way. Because all of them are agricultural fields of some type, I just set them all as one general class as agriculture. Select OK. Now, I can first go to the ground truth import option. So I'll select import, which will load the import ground truth window. I will select the ground truth shapefile. And the important point is that this can be shapefiles or PIX files. Choose the layer, the ground truth, and then choose the field that I want to use for that contains the classes. So I'll choose class. I can set how I want or what I want to use the ground truths for, either for the training algorithm to actually train this classification algorithm, or use it for accuracy assessment. I will then open up the training site. There we go. I will open up the training site editor, and I've already collected a number of training sites. But if you remember, all these ground truths have now been classified in their segments, the ones that are within the area of interest. I have gone and created a number of different classes. Developed land, which contains all those agricultural fields, but important, I've also collected a number of urban regions, and we can zoom in and see. This is the whole city. This is called Sorel. I collected water, some swamp regions, and then 3 different wetland classes. And now this is important. If we zoom into that area, that large wetland area, we can see that there's some orange speckle, but also we can see in areas of purple speckle. And those two are 2 different wetland types. The orange is cattails, or wetlands that contain cattails, while the purples actually contain scirpus. But there are areas that contain a mix, so I've also created a Wetland Mix Class. Just to showcase how we can collect classes, I will select a number of segments and set them as Wetland Mix. And these will be then assigned the Wetland Mix class and be used in the training of the supervised classification. So it's always a good suggestion to get a wide variety of different segments to cover the range to help bolster the training algorithm. Once I'm satisfied, I'll click Close and choose the Supervised Classification. Here, the first option with the Select allows me to select all the attributes in the segmentation attribute table that I want to use for bolstering the classification, and I've selected all of them. This contains both the quad pole attributes from the July and the April data set. Select OK. Choose the training field that contains all the training classes, and it's called Training Sites. Choose an output class field. I'll call it Supervised _class. Choose the classifier type. For this, I'll leave it as default radial basis function, and then run the process. The output will then look, as we see out here, all these segments have now been classified based upon the training sites we provided. But watch out, there are a few misclassified segments, as we see over here. These segments have been misclassified as developed land when really they should be classified as swamp or water. And well, we can't have that, can we? So we need to perform some rules and conditions to reclassify them to their norm or to the correct class. So I'm going to choose our rule-based classification operation. select the segmentation. And now here is where we can create rules and conditions. We have a on-the-fly WYSIWYG viewer, which will actually highlight segments that will be affected by the rules and conditions that we're going to build. For that, I'm going to click Specify Condition and open up the Attribute Visualization tool. Just going to put that all the way to the bottom. And now I can choose the class field, the field that contains all of our classes. So as I wrote before, it's Supervised Class. The different classes we created, which will be class filter, and what do we want to change? We want to change segmentation or segments that have been misclassified as developed. And what do we want to use? We're going to use mean July. We're going to use some texture measures. I'm going to scroll down and choose the minimum, change the minimum. And we can see as I'm already running this, all these segments are changing. I'm going to change the maximum all the way to 10, just until all the segments I want to change are highlighted. Great, I'm satisfied. I can click OK. This condition has now been loaded, but now I'm going to choose the class field again and populate the inputs. So class field is Supervised Class. What do we want to change? The class filter, we want to change the developed land into swamp. So what is the new class? I'm then going to run the process. And voila, those segments have now been reclassified. Now, once the user goes through and performs rules and conditions and changes and is finally happy with the segments and the classification, they can do the last step, which is the post-classification editing. Here we can run an automatic dissolve, which will dissolve all the segments by class into larger segments. Also, we can choose the dissolve option, choose the vector, select the class we want to use, or the field we're going to use to dissolve into. We're going to dissolve into the supervised class field. Set an output. I'm going to set it to dissolve. Give the output our layer name. Run the process. I'm going to minimize. And now we have the reform shapes of the different wetland types and other land covers. And this can then be used for further analysis and management procedures.
Great, thanks, Jason. Okay, so one of the things that we're working on, this isn't something that's released right now, but it is something that's coming in a very near release. We are working on algorithms that can automate a lot of the steps that you saw Jason doing manually through the interface. So the segmentation step, we are developing an algorithm called OASEG. The part where Jason was attributing the polygons with the different information, that is another algorithm that's being developed. And then when it comes to the actual training of that data set to perform the next part, which is classification, when we work with a template image, so over here we're kind of representing a template image that has multiple channels, what we will be capturing is a hyperplane learned model based on how it's been trained. So this is a text file that's sitting on disk based on the representative areas that you've trained the algorithm on. And then you can provide that to the next algorithm, which is the classification, which is SVM classification, and then the dissolve. So really what this will allow you to do is to massively process much larger data sets in an automated fashion. So I just didn't want you to get the sense that the tool is only available within Geomatica. That is the case right now, but it's something that we're actively developing and we'll be releasing very, very soon. And it will also be available for optical and radar data. So just want to draw a few conclusions, if you'll permit me. We have released the 2018 software. It was released at the beginning of October, so it's been roughly 2 months. And OBSAR, or Object-Based Synthetic Aperture Radar, is a new capability that was added at that time. So as you can see, hopefully, it really allows you to work with radar data, even some of the more difficult radar data to work with, which is fully polarimetric data sets, which is what Jason was working with today. We're trying, or one of our design goals is to make that type of data accessible. And hopefully we've achieved that goal. The ability to import external ground truth data simplifies the training site collection, and we can also refine different areas by using sub areas for processing, for testing. We just want to sort of close things off. There's a few more things to say, and then we'll open up for questions. But one last question here. I'm just going to launch the poll. So we are actively developing this software, and our development team would love to get feedback from you as to what should be next. So we're asking you, the market and the community, the user community, if you're using radar data right now, and if you happen to be using our tools, what should we be adding that you're not seeing or that's difficult to do right now? So support for all sensors, and maybe define that specifically, what sensors. Improved fusion of radar and optical, automatically processing large data sets, as I mentioned, is something we're working on right now. Multitemporal analysis, or if there's something else that we've missed, by all means, throw that in and into the questions panel, and we'll be able to track down what it is that your suggestion was. So that would be great. So looks like a good number of you have voted, so I'm just going to leave that open for 3 more seconds. So 3, 2, 1, and I'll share the results with you again so you can get a sense. And it looks like multi-temporal analysis is definitely an area where you're looking for us to add more capability. Fusing with optical imagery is also very important, followed by automating for large data sets. So that's very interesting info. We really thank you for that. I just want to throw up a few more things on the screen. So we are planning a webinar series, as I mentioned. You're in the middle of it right now. This is the first detailed webinar that we've executed, specifically targeted on object-based image analysis for SAR. And as I mentioned earlier, there's DSM True Ortho. There's going to be multi-sensor mosaicing. There'll be ARD and multi-temporal analysis coming further down as well. And you can definitely download our software. Just go to getgeomatica.com. We offer a trial license, and if you are working on something and you're just kind of scratching the surface and you want to use it for longer, we're always open to receiving an email from you. We'd love to hear what you're doing, and we can extend your license for a longer period of time as you're sort of conducting your research or making your decision about which tools to use and how to implement your workflow. So we are open for questions. I'll pop open the questions panel at this point and see if there is a specific question that we haven't answered. We have been answering the questions throughout the webinar, but happy to read out a few of them in terms of what was asked. And feel free to type more in right now if you're not sure what your question is, go ahead and type it. But basically, we had a question about the type of data that we were using in the demonstration. So it was a RadarSat 2 fine quad data set, which is multi-temporal. And it was basically 2 different images collected exactly in the same orientation. So the incidence angle was the same. And what separated the 2 images was just time. So they were collected roughly 4 or 5 months apart. The resolution on that data set was 5.2 meters in azimuth and 7.6 in range. We have a question about Object Analyst, if it's a separate package. It is a separate package. It's an add-on. It's not terribly expensive. If you'd like to get pricing, by all means, get in touch with us. One of the nice things is if you're planning on working with radar data, what you can do is you can simply use the Object Analyst module, and you'll get a lot of the capability that's in our radar suite, which is aimed more for a full radar processing capability. So if you're running a lot of different radar workflows, then you go with our radar suite. But if you're trying to replicate what we did today, you can pretty much get away with a standard license of Geomatica, and then you can add the Object Analyst module, and you'll get a lot of the pre-processing capability specific to the Object Analyst workflow built in. So it's a nice option if you're just trying to work with SAR data and get your feet wet. So the question about whether the segmentation operates on complex data, absolutely it does. We maintain the data. We can maintain the data in the slant range, and we can also maintain the data in complex format. So at any time you can run an algorithm called PSIQ interp. What that does is it converts the complex data to intensity, and if you want to work in intensity units, you can do that. But you can definitely do that. There's a question about the availability of the capability that we showed today in the trial license. Absolutely, it is available. So if you download it today, you can open up the Object Analyst panel just like Jason was doing. You can point to a Sentinel-1 dataset or a RadarSat-2 dataset or any of the datasets that we support. And to the extent that we support those datasets, you could conduct the analysis as we've demonstrated today and is documented in our technical documents. There's a question about parent and child. So I think the question relates to multi-level segmentation. So this is a capability that's been that is quite useful. So it is available within Geomatica right now, although it is a little bit cumbersome. We don't have it built in, so you can't ask for multi-resolution segmentation by default. Although it's pretty straightforward to establish a relationship between two different vector data sets. But it is a capability that we have repeated to our development team, and they're definitely looking at it, and it's on the roadmap. So that's something that we're definitely looking at. Once again, one of the design goals is to make object-based image analysis accessible and straightforward. So we're not looking to create a hyper-complex system that makes it very difficult to even begin a session and understand how to run data sets. So that's a fundamental goal in our software. So although there are feature-rich capabilities out there in the market, our goal is not to develop the same thing that's been out there for many years. We're really targeting rigorous analysis, but a little bit more straightforward to work with. I think that's about it. There's a few other questions popping in, but I think at this point I'll call it a day. And I'd like to thank you one and all for making the time to be with us today. You're very many of you are here with us today, so we're glad to see that. There's a lot of people that attended and a lot of great questions and a lot of great interaction. So thanks once again, and have a great end of your day.